Hi, everybody. My name's Andy McMahon. I'm really delighted to be here as part of Data Scotland's Scottish Summer 2021, which I think is an absolutely excellent initiative, showing off talent across the Scottish data community. Some of you might know me from the community. I am a data scientist, machine learning engineer with a few years' experience in a variety of different areas. So previously, I've worked in oil and gas logistics, I've worked in energy and utilities, and most recently in financial services. So I've got experience across those domains, working with teams to develop machine learning solutions that we take through to production, and often work to very large scales. So my perspective has always been of someone who's very interested in algorithms, but also interested in how you deploy those algorithms at scale, how you analyze big data, but also how you really build services and products around the data science knowledge that you have when you apply those algorithms. So that's why the title of my talk today is A Whirlwind Tour of Machine Learning Engineering. I'm going to try and give a very high level flavor of some of the things that I often think about when I'm working, and some of the things I'm really interested in. And it's all centered around taking models through to production. So hopefully you find something in here of interest. So we just kick off with some basic stuff that I think we can all agree on. So first of all, science is not the same as engineering. So what do we mean by that? Well, data science, machine learning engineering, they're two different sides of a similar coin, but they really try and have different things they go after. They have different outputs they're aiming to make. So on the science side, data science side, you're trying to analyze and understand your data, apply it to solve your business problem, really translate subject matter expertise and data and algorithm knowledge through to something that melds together quite nicely. On the engineering side, what you're often trying to do is build products, services, solutions based on that knowledge found through the scientific enterprise. So it's a bit less about experimentation, a bit less about modeling. It's a bit more about really optimization, about scale, about robustness, about testing. So although they're complementary to each other, and I would absolutely not say that one is more important than the other, I think they're both integral to the whole enterprise of doing data. I do think they are slightly different things, and that is important. And it's an important thing if you're either leading a team or part of a team that's tasked with not just building data science models, but taking them through to production. The next thing I would say is that we'd probably all agree that machine learning programming, building machine learning models and solutions is not the same as traditional programming. So there's always a bit of contention when people try and make out that it's very mathematical and it's something you can't do unless you have a PhD. I totally don't believe that, but it is a different skill set, it is a slightly different focus. So whereas in maybe traditional programming, there's more examples maybe of kind of paths to how to get things into production. It's been a tried and tested path. For example, if you're spinning up a website, a web application, that's well trodden. There's still lots of innovative things to do there, absolutely, and new tools and technologies to use, but it's a lot more mature, and that means there's a lot kind of more knowledge to draw on when it comes to processes, tools, technologies, and how to apply them. Whereas on the machine learning side, everything's a bit newer. Machine learning's been around for decades, but machine learning in industry is still quite a new exercise in comparison to maybe more traditional programming methods. So we just have to appreciate that although it's not required you have a PhD, there is some parts of it where you do have to have a bit of understanding of algorithms and how data work in a way that's not as important maybe in traditional programming, or it is important, but it's just maybe not your focus. So it's just important to bear that in mind as you go through your career in this sort of area. And then one final thing I think we probably agree on, if we've any experience of working in industry and building software, is that going through to production is not an easy thing. So even in this PhD comics cartoon, where basically the PhD supervisor is satisfied by just being shown some data, that's not going to cut it, is it, when we try and build a service in the enterprise and try and serve our colleagues and our customers. So we just need to bear that in mind as well, that the ask of us when we take something through to production is a bit more stringent than if we're simply experimenting and trying to play in a sandpit or try and build some initial proof of concept. It's a very different ask to take that proof of concept, build on it, and really produce a service or solution. So those are kind of some of the points that I think we'd all agree on as a good baseline for moving forward to this, and maybe starts giving a flavour of why machine learning engineering has really risen as a new type of role or a new type of discipline over the past few years. It's complementary to data science, but it is slightly different. But it'd be good at this point maybe to recap at a high level why we do machine learning. Why do we actually do it? So in a nutshell, I say, and there will be counterexamples, no doubt, that everyone will be able to come up with. But I think broadly, we could say that it's all about supporting decisions. So it's all about using the data that we now have swathes and swathes of. We have data stored in so many different formats across so many different domains, and we can now integrate and analyze them at scale in a way we couldn't possibly before. And we now have the capabilities and democratized capabilities, I would say, to actually model that data in a way that can drive value. So it's really at the heart of it, it's all about making business decisions, organizational decisions, could be policy decisions, but it is at the heart decisions. And that's maybe why some people would recognize that data science, machine learning is sort of inherited or complementary to the traditional art of decision science itself. So the idea here is really that data feature models in an iterative way. You then run predictions that help guide people to make the appropriate decisions. But given that high level view and the things I mentioned earlier, what do we need to think about that's a bit different for deployment, which, as I've said, is really what's at the core, the heart of machine learning engineering, as opposed to maybe data science more broadly? So what do we need to start thinking about for deployment? Well, I've tried to over the past while really condense down my thoughts on this and really what I think is the most important aspects to think about and bear in mind when we talk about deployment. And I've really kind of think it's down to these four things. I've called them the 4 Ps. Everyone likes a bit of alliteration. But I think broadly this covers everything that you need to really start tightening up your approach to deployment and productionizing machine learning solutions. So you've obviously got people, you've got the process, you've got the product you're trying to build, and you've got the patterns you work against. I'll go into all of these in detail in a second, but I think if you just kind of think about these holistically, these should cover almost every aspect of your data science, machine learning, engineering lifecycle. So as you go through ideation, proof of concept, through to further development and eventually productionization, you're going to leverage your people. You're going to need to upskill them, make sure that you have the right blend of people. You're going to have to work to a process. You're going to hope and make sure that that process is robust and fit for purpose. You're going to have to work against patterns and not reinvent the wheel every single time. Otherwise, you'll never deliver on time. And at the end of the day, you have to remember that it's all about building and serving a product to a colleague, a customer, and to help make those decisions. But it really can't be something that's done haphazardly and on your own. It has to be done by teams of people working to a good process, executing against robust patterns, and building great products and services. So I'll now dive into that a little bit more detail and unpack it. So first we'll get people, right? So this is the famous Venn diagram that you've probably all seen that says that data science is really the intersection of these 3 disciplines: computer science, maths and statistics, business and domain expertise. And then you have these kind of bits in between. You see machine learning, data analysis, traditional software. I've never liked this Venn diagram. If you've heard me talk elsewhere, you've probably heard me have a go at this diagram. And that's basically because I don't think it's fair to expect one person to embody all of these, at least not in equal parts. So it's not really fair for someone to be an expert in computer science, maths and stats, and business and domain expertise. I think absolutely you can have knowledge of all 3. You could be great at all 3, but you're probably going to have some area of focus that probably spans the 2 of them. So I think when you start thinking about your team, you really have to understand that it's all about blending what you need across multiple people. It's not about finding those one unicorn, that one unicorn that's really going to solve all your problems. That's a bit of a fool's errand. I think what you have to look for is really a team shape, a team composition that really covers all of these aspects. So you should maybe start thinking about things like, what programming languages do you want to use to take through to production? Is it going to be Python? Is it going to be Scala? Is it going to be something else entirely? But basically, what's the computer science elements you need to start thinking about? How does that feed into this? Do you have that base covered? You have to start thinking about when you get your people and you're blending across these different domains of expertise, how are you going to organize them? So are you going to have a traditional kind of team lead structure feeding into seniors, feeding into juniors? Are you going to have a much flatter structure? Are you going to work in squads? Are you going to work in a hub and spoke model? All of these are absolutely fine, but it's really about designing your team structures for the appropriate projects, for the appropriate products you're trying to build, and also so that you really leverage the complementary expertise within your team. You then have to think about the wider technology stack you're going to use. Do you have the skills for that? So not just your Python and Scala question, but really, are you going to be working in the cloud? Are you going to be working on premise? Are you at the stage of your journey where you are going to really deploy something at scale that's going to require thousands of containers or managed by Kubernetes? Or are you going to actually be doing something that's really a single containerized web application that's not going to have much traffic? These are quite different asks, I think, and they'll allow you to leverage people with different skill sets. And then finally, the thing not covered in this Venn diagram, but is potentially, to me, the most important skill is communications. Who in your team is going to have those communication skills that's going to help translate the business problem into the data domain and then back again? Who's going to be the one who presents at stakeholder meetings and helps really articulate what you're doing and how you're doing it, and helps convince people that you know what you're doing, that you'll build robust solutions and also deliver on time? So that's quite an important aspect. So you can see that this people question is, I think, potentially the most important and also one of the most complex to get right. And then we have to really think about what we're trying to build. So as I mentioned before, it's about products, it's about services. So here I've got a diagram taken from a paper from Google called Hidden Technical Debt in Machine Learning Systems. And basically you can see here that there's lots of different boxes that are really important to think about when you build a product that's different from just building a machine learning model or some data analyses. And that's not to say it's harder, it's just different. It's a bit more involved. There's more aspects to think about. And you can see that basically in all these boxes, there's only a tiny little box in the middle that's actually about ML code. The rest is about the surrounding infrastructure, components configuration, resource management, all of these different things that feed in and leverage or use that ML code are actually quite disparate and separate. And that's really important, because that's really where the ML engineering tool set comes in. It's about being able to appreciate and understand that ML code in the middle, contribute to it, optimize it, but also see the bigger picture, how it links in with all these other tools and components. That's really important. So when you're building a product, you're really thinking about this holistic picture, and that's where your ML engineers and MLOps functionality comes in. And you have to bear in mind that there's a few things that are different from products versus, again, these kind of ad hoc analyses or models that can also inform decisions and are very important, but are just a bit different. So products, the products you use to work, right? They obviously fail, but they fail so few and far between that when they do fail, you get really annoyed. So when your iPhone stops working, you get really annoyed because normally it works. So the point is for that as an engineering function and engineering group, you have to really test to the point that you know your solution is going to work in production. Your products get delivered. So again, when you order something from an online shop, it gets delivered to you as a product. It's very clear what it is, what it does, and it's what you ordered. So that means you have to really be clear about what the value add you're bringing is and what's new every time you do a project. So don't reinvent the wheel. Don't think you're the first team or person to ever try doing some monitoring, serving infrastructure, data verification. These have all been done a little bit before. Not as much as in traditional programming, as I mentioned. There's maybe some newer challenges there, but there's a lot of things where you don't have to reinvent the wheel. And there'll be aspects in there where you have to do something a bit bespoke, a bit nuanced, specific to your domain maybe, and that's where your value add and effort should be, but don't reinvent the wheel more generally. Remember that products come in a variety of shapes and sizes, and that basically you almost never deliver a product and then forget about it, or you shouldn't if it's going to be a well-used one. If it's well used with your colleagues or customers, people will come back and want more. They want additions. They want the shape of that product to change. So really build for flexibility. So think about boxes, containers, think about architectures and patterns, which we'll come on to, that allow for that flexibility. And then kind of quite nicely, that segues into the idea of patterns. And what I mean here is really architecture patterns. So here we've got two links. to some examples from Google Cloud on the left-hand side. So they publish 13 sample architectures on their website that are really good at showing you how their different tools and solutions hook up to provide different services that you can build. And similarly on AWS on the right-hand side, Azure and other cloud providers will also have the same thing. But they're very open about what these patterns should be. So there's really no excuse for not having that knowledge to hand and not doing that research you need beforehand. So if you're building a streaming application that's going to do classification on the fly, look into that. Someone will have built these patterns you can work against. If someone's going to do a big batch job that's going to run over millions and millions of rows every day, and you need to understand the best way to do that and what tools to use, work against these patterns. Again, learn from the best, see what's there. Don't reinvent the wheel, and really push that value add where you can see that little bit that has to be different for your use case. So reuse, repeat, recycle, get good patterns down, use them again and again, and make sure everyone on your project team and even in the wider community that you're servicing, so your colleagues and customers, make sure they understand as well the patterns you're working to, at least at a high level, so that they know how everything hooks together and why the solution you're building is ultimately going to solve their use case. Then process, so the second last one of the 4 Ps. So basically, how are you going to work as a team, as a unit, and how are you going to build that end product that we just discussed? So there's kind of 4 stages that almost every machine learning project that I've worked on that we've taken to production has fallen into, has used. They might be called different things. There might really be 3 in some cases. There might be 5 in others, maybe 10. But I think you can always broadly bucket it into these different activities. So the first one is really about discovery. So how do you understand the data problem? So that's really where you leverage that communication skill set I mentioned you should have in your team. So you'll do lots of things like, PowerPoint slides, Word document reports, some initial analyses, phone calls, IMs. And we basically understand the challenge that you're trying to shape up and fight. And then define your end goal. You have to define the KPIs you're going after, the baseline performance that your customers will be happy with. You probably want to sketch an MVP implementation using some of those patterns I just mentioned. Even back of an envelope is great. Help start shaping up what the scope of the problem is going to be. And then you should always summarize for sign off from someone from the business. They should be happy that this is going to solve their problem in some sense, and that you can always be agile and iterate and adapt through that. But we should have a good direction of travel agreed at the beginning. And again, broadly, discovery, I've called it. It could be called a variety of things, but I think often this activity should come first. You then have a set of activities where you could broadly classify it as proof of concept development. So doing your exploratory data analysis, your identification of what the blockers of the project will be. So if you do the analysis and you realize actually the data you needed isn't accessible, or you do the analysis and find out that it's impossible to build a classification model with the appropriate recall, you can do that through this stage in this proof of concept development. You can identify other project risks. So it might be that piece of technology you really thought was critical to delivery isn't actually available in your organization. You can try that and highlight it at this proof of concept level. You can start building that bare bones skeletal implementation based on those patterns we mentioned, and really start articulating how you're going to solve this problem with a bit more meat on that skeleton. So you're going to start having some data flowing through the system. You're going to start having some results from your models. You're going to start having some results you can present back. So you're going to have that evidence that the solution is viable. And really that requires sign off again. You've not just done a discovery and a high level implementation design, you've now started to actually analyze the data and build the models. You then go through to the 2 sections where I think ML engineers are critical. The first 2 are really where data science can play a bit of a stronger role potentially. But here is where the ML engineering and MLOps side of things really comes into play. So when you start actually developing the solution, your tool set is going to change a little bit, and you should really start thinking about how you work. So are you going to work in Scrum? Are you going to work in Kanban? Are you going to work non-agile? Potentially, but are you going to how are you going to build the stuff as a team? How are you going to do version control? So I think this is so important. Your machine learning software is software at the end of the day. It should be under version control. And in fact, you should extend that idea to build your models under version control using tools like MLflow or other tools that are out there. So basically, how are you going to control the changes within your code base and your model base so that you can ensure both lineage and and you can audit what's going on, but also so that you never lose any work, and so that you can really start developing quite sophisticated strategies for building up your solution and working in parallel. You should bring to bear some of the great things from software development other than Git strategies. So unit and integration tests, really start thinking about how you envelop testing as part of this. So tools like PyTest are absolutely excellent, very easy to use for those kind of fluent in Python. There's the equivalents in Scala and other languages, but basically simple libraries that wrap unit testing functionality to allow you to actually do things like test-driven development if you choose to do so. That's really important for building that trust in the solution you're developing as you go along. And then I think you can start from this doing baseline performance tests and getting some results of a prototype, well, prototype plus one essentially solution. So it's not just kind of a bare bone, some notebooks stuck together. You're now actually saying, here's that pattern we showed before, fleshed out, each of the components actually talking to each other, doing those integration tests, showing how data and results will flow through end to end. And then you can start defining baseline performance. So performance here is not just model performance as in the POC, but actually solution performance. How is your memory footprint? Are you doing things within the appropriate timescale? Are you hogging resource if there's shared compute, for example? So really starting to think about these performance metrics in a wider sense that's appropriate for developing a solution. And then finally, you move to deployment. So the ML engineer will start thinking about how do you package it up? Are we going to write a standard Python library that we distribute with a Conda environment? Are we going to containerize in Docker? Are we going to then scale up those containers using Kubernetes? Are we actually doing something so lightweight we can deploy as a cloud serverless function like Lambda? Or are we going to do something like a web application, a very simple Flask app shielded from the rest of the world by something like Google's container engine or Google App Service? So basically, you start thinking about what infrastructure you're going to pull together for the actual end deployment, where you're going to host things, where you're going to run things, what your scheduling like, and basically tidy up the final pieces. So make sure that your performance monitoring is in place. You're going to know and have alerts if something goes down. Know that your documentation is really robust so that people understand what's there if they need to help fix it. Start working, or you should have already been working on this really, but basically this is the proof of the pudding part where your CI/CD pipelines can come in. So if you're working to DevOps, which a lot of people will be now and should be, then you have to really see here that your continuous deployment pipelines are actually working. So you're not just doing the integration steps you've maybe done for your automated testing before, but you're now pushing things through to deployment using CI/CD principles. And that'll just make things more robust, tick along more nicely, and help to automate a lot of the steps. So that's quite a lot of information, but I think process is probably the one where most people fall down on. So I like to expand on that quite a bit. So in a nutshell, I think my talk has really been about how ML engineering as a discipline, as a focus area within data more generally, is really critically important, and it's complementary to the other disciplines like data science and data engineering. And hopefully you can see how that is complementary. I think it has its own unique challenges, but it also brings its own unique benefits if you invest in the skill sets of ML engineering for your people, or in hiring ML engineers and giving them the tools they need to succeed. So that's it in a nutshell. Really appreciate you listening to me drone on for 30 minutes. So I'm really, really happy to have been here. If you want to get in touch, or where can you find me, is basically I'm on Twitter at Electric Ouija. I'm on LinkedIn, Andy McMahon. I'm on GitHub at AndyMix629. I have a blog, electricouija.com. I'm going to put the slides up on GitHub. And I also have a book coming out later in the year, published by Pact, called ML Engineering in Python. So please watch out for that. And thanks very much for listening.